All right, let's get our notes out. If you haven't turned your quiz in, I need you to do it right now. Turn your quiz in, and we are on the back of page 57, and we are ready for number 11. Now, when we say how many four-letter call signs are possible, we mean like on TV, WTHR. Or WIBC. Those are the call letters of the TV and radio stations. So how many are possible? Four-letter call signs. How many are possible? Now, are there any restrictions? No. It says every letter is allowed. So if every letter is allowed, then what's the answer going to be? 26 times 26 times 26 times 26, right? There are no restrictions. You can use any letter. Now, when you type that into your calculator, you can type it in 26 times 26, da da da, or you can just say 26 to the 4th. Whatever way you want to do it. What is the answer? 400 and some thousand 976. Right? Okay. So that's what you write down as the answer. Now, number 12 says, same question, but no letter can be repeated. So we still have 4 choices, or 4 blanks, but now we can't repeat a letter. So what's going to be different? 26 times 25 times 24 times 23. Now, that is not 26 factorial. There's no shortcut here. You just have to type in that multiplication. Did you get a smaller number than you got on this one?
Yes.
Of course you did. Because the more restrictions you put into the problem, the fewer options there are going to be. Does that make sense to you?
Yes.
Okay. Now, number 13, same question. Now, no vowels are allowed. Now, we're going back to number 11, which has no restrictions on it, except we're saying now you can't consider vowels. And for purposes of math problems, there are 5 vowels. A, E, I, O, and U. I understand the weirdness involved with Y sometimes, but no, A, E, I, O, and U are our vowels. So 21 times 21 times 21 times 21. That would be the answer to that one. So that would be like, I don't know, W, D, F, G or something. That would be no vowels in that thing. All right, number 14, same situation, but now no vowels and no repetition. No vowels, no repetition. So what does that mean?
21 times 20 times 19.
There you go. These are very easy if you, first of all, remember that the blanks represent choices. It doesn't mean I'm putting 21 letters there. It means I have a choice of 21. And then the second thing is you just got to read the problem. You got to read very carefully. All right, number 15. If a baseball team has 9 starters, how many batting orders are possible? So here is, I'm the baseball coach. I got 9 kids going to line up and play the game, and I need to put together a batting order. 9 factorial. That's it. When you put a batting order, aren't you basically just putting them in a line?
Yep.
Lining them up and saying you're first, you're second, you're third? That's 9 factorial. Now, 16 says, what if the pitcher has to bat last? Okay?
Isn't it like 8?
Now, if the pitcher has to bat last, then that means there is one choice for that blank. Would you agree with me? If I'm the pitcher, then I'm out of the mix. I'm last, period. So how many kids are left? 8. So this is going to be 8, 7, 6, 5, 4, 3, 2, 1.
So it'd just be 8 factorial.
That's 8 factorial.
Because
That is 8 factorial, because timesing by this extra 1 isn't going to change anything. But you can, if you're uncomfortable with that, just type it in. But that would be the same as 8 factorial. All right, now 17. Pitcher bats last, and the best hitter bats third. Now, I heard some of you think you already have the answer. Here's the pitcher. You have one choice for the last spot. The pitcher goes there. Now, third is the best hitter on the team. There's one best hitter. You have one choice for that spot. So now when you're putting together the rest of the blanks, how many kids do you have to choose from? 7. So 7, 6, 5, 4, 3, 2, 1. I heard somebody say 7 factorial, and that looks a little weird, but isn't that really 7 factorial? Remember, timesing by 1 is irrelevant. So that's 7 factorial. Very, very good. All right, now 18 introduces just a bit of a new scenario, because it says we're going to make 1-digit, 2-digit, and 3-digit numbers. So we really have 3 separate problems. So we're going to look at the 1-digit numbers first. There it is. Yeah. How many options do I have for 1-digit numbers? 6. Done. There's 6 numbers to choose from, so I can make a 1, a 2, a 5, whatever. Now, what about 2-digit numbers? I'm thinking of this as a separate problem. 2-digit numbers. How many options do I have for the first digit? 6. And how many for the second digit? Wait. Can't 2-digit numbers like 22? Does 22 count as a 2-digit number?
Yep.
Yeah. So there's no issue with repeating, so there's 36 of them. So there were 6 1-digit numbers and 36 2-digit numbers. Now, I'm also going to make 3-digit numbers. So how many options do I have there?
Don't write it. That's the devil's number.
Wouldn't that be 216?
That is the devil's number.
216?
No,
666.
Oh, I'll put time signs. Okay. Now, obviously this was one question that was really like 3 smaller questions inside of it, but I need to come up with one answer. So what do you think I'm going to do with the, who said Adam? You're exactly right. I'm going to add these together. And the reason that I am adding them is Jalen and Judah. We do not have much time together, right? So let's focus. I'm going to add these together because I have 6 1-digit options, I have 36 2-digit options, 216 3-digit options. So all together means add them up, find the total. I'm going to total it up, and what do I get?
258.
258. I am going to add those up. Kennedy, turn around, Jack. Let's be quiet. All right, here we go. How many 5-letter words, and words is in quotation marks because these aren't going to be really words. Just how many ways can we arrange the letters of the word Chevy? 5 factorial. Whoever said 5 factorial, you are right on target. How many letters are there? 5. How many ways can I arrange 5 things? 5, 4, 3, 2, 1. 5 factorial, so 120. Now what about pre-cal? That'd be 6 factorial, which is 720?
Yeah.
So the answer to 20 would be 720. How many social security numbers are possible? And I don't know if you know your social security number, but it looks like this, right?
Mine's 30. You have letters?
We don't say your social security number out loud, oh my goodness. No, social security numbers do not have letters. They have only numbers.
They might have to start adding them.
Now, it says that every arrangement is possible. So that means you can use whatever digits you want.
Even letters?
Digits. How many choices do I have for the first one?
9.
Any digit is possible.
So 9. A lot.
How many digits are there? 10. There's 10 digits. So you can use any digit. All right, guys, you're going to be held accountable for this material. I don't care. If you don't want to listen to me, then you can go figure it out on your own. But if you want me to continue, you're going to have to be quiet. And Jalen Buford, I want you turned around in your seat. I don't want to see you looking at the back of the room one more time. Now, I know probably in real life that we don't have social security numbers that start with 0. I mean, I don't know. I'm not a social security expert. But I'm reading the problem, and it says every arrangement is possible. How many digits are there in our number system? 10. So if every one is possible, then I have 10 choices for the first blank. How many choices do I have for the second blank? 10. Boys and girls. My social security number has repeated digits in it. I bet yours does too.
3 6s.
That's good to know.
Actually, yes, mine is.
There are repeated digits.
Hey, what is it? Tell us.
Don't. Kids, we're on video, so we don't need to be broadcasting your social security number. If we put restrictions in the problem, it will say no repeats allowed, no zeros allowed, or whatever. It will say that. When it says all arrangements are possible, that means you can put any number in any of these blanks. Now, that amounts to 10 to the 9th power, right?
That's a lot of zeros.
That's a lot of zeros. However, that represents the total maximum number of social security numbers there could be. You could not possibly have any more with this format. That's the most. So when we start taking out different arrangements, for example, there probably isn't anybody with all zeros, right, in your social security number. Probably there isn't anybody with all of the same anything. Probably any of those. So when you start pulling out the ones that they don't want to use, that number's even going to go down, and there's going to be fewer social security numbers than that. But that is the maximum number. All right, number 22. We talked about this a little bit yesterday. How many phone numbers are possible in the 317 area code? So we have, think of your phone number, and again, don't say it out loud because we don't need random people calling you. But think of your phone number.
Hit me up.
Oh, there's so many randoms calling me. I get calls from the Netherlands.
All right, so here we go. We're all agreed we're going to do the 317 area code, so that's done.
7.
If there are no restrictions placed, then how many numbers would be possible? 10, 10, 10, 10, 10, 10, 10. And that would be 10 to the 7th. Now we know in reality, that would be the maximum number of phone numbers, which is 10 million. We know in reality that they don't start phone numbers with zeros. This can be a 0, but there's no phone number 018, something like that. So when you start taking the restrictions, that 10 million goes down, and that leads us to what we talked about yesterday, where we need to create new area codes to get more phone numbers accessible.
So if you wrote it out completely, it would technically look like 1, 1, 1, 10, 10, 10, 10, right? Like the 317 if you wrote it out. Like,
yeah. Okay, now, we must talk about this next problem. There are 3 things that we need to address today, and one of them happens in this next problem. Look back up at problem 19. When you answered problem 19, which you did very quickly and you got it absolutely correct, you said 5 factorial. And you said 5 factorial because there are 5 letters, right? That was easy. Well, how many letters are there in the word pre-calculus? 11. So we're going to start with 11 factorial. The rule is, and listen to me, we've already talked about this a little bit. If you have 9 things, they can be arranged 9 factorial ways. If you have 5 things, they can be arranged 5 factorial ways. So 11 things will be arranged 11 factorial ways. The problem is what? What makes this word different? Some of the letters repeat. So this is how you handle that. It looks like in this word I have 2 C's, so I divide by 2 factorial. That's the C's. But wait, I also have 2 L's, so I have to divide by another 2 factorial. Oh, but there's 2 U's, so I have to divide by another 2 factorial. Now, there is no way to simplify 2 factorial, 2 factorial, 2 factorial. I mean, it equals something, but don't say 6 factorial or 8 factorial or something goofy. It's 2 factorial, 2 factorial, 2 factorial. When you type this into your calculator, you're going to type 11 factorial divided by parentheses 2 factorial, 2 factorial, 2 factorial. Or, if you want to simplify it, you can figure out what 2 factorial is. What's 2 factorial? 2. It's 2 times 1. So you're really dividing by 2 times 2 times 2, which is 8. So 11 factorial divided by 8. You're always welcome to do that. Now, we cannot talk about this word. Well, yeah, the next question. Let's talk about Mississippi. How many letters? Oh yeah, I better type that in to make sure we're getting the right answer.
I got 1.375.
Well, you could times 10 to a power.
You know what? Maybe I did. Maybe because I didn't put in factorial.
Okay, so the answer here is 4989600. So this is the answer you should get when you type this in on your calculator. Make sure you're typing it in correctly. On the quiz that we take, if you have the setup right, you're going to get 3/4 credit for the setup, and then 1/4 credit for the correct answer here. So if you can't type it in, it's going to be -1/4 on every one you mess up. So let's make sure we're typing those in, everybody getting it right. Now, Mississippi. Start by counting the letters. How many letters are there in Mississippi?
11.
So we start with 11 factorial. Now, we've got 1, 2, 3, 4 S's, so that's 4 factorial. I do each letter individually. So there's 4 S's, 4 factorial. There's 4 I's. So that's another 4 factorial. There's 2 P's, so that's a 2 factorial. Now I am going to just type this one in. It's quicker for me just to type it in, but I got to use those parentheses. So 11 factorial divided by parentheses 4 factorial. 4
It's in PRB.
factorial.
PRB. Good at math.
So, oh, this is a much smaller number. This is 34,650. So that's the number you want to end up getting when you type that in. So I said we were going to talk about 3 new things today, and one of the new things is, how do we handle repeated letters, repeated anything? I mean, there are other cases where you can have repeats. How do we handle it? We divide by the repeats factorial, and you do each repeated item individually. Okay? Now, 25. Here's your first and your last initials. Like Mason, that would be MP. Corey would be CA. How can we be absolutely sure that at least 2 students at Cathedral have exactly the same first and last initial? Because the only options are 26 times 26. And what is that? 676. Well, wait a minute, boys and girls. What you have just shown is that the total number of 2-letter initial options is 676. How many kids are at Cathedral? 1,100. Well, if there's 1,100 kids here and there's only that many options, then obviously somebody's got the same initials, right? Has to. Does that make sense to everybody? Gotta have the same initials.
So this is all in probability.
It does. We're headed to probability. Not today, but that'll probably be our next class. Now,
Percentages, right?
Probability?
now,
No, it's
here
like
is
4 to
the
1.
second
4 to
thing.
1.
Shh. Guys, this is the second thing that we're learning today. This is big.
What's the probability of hitting?
I need you to read question 26,
5 times like 24 sides.
A and B. And I want you to tell me in question 26, A and B, if they are the same problem or if they're different problems. And if they're different, you have to tell me why they're different. I know I've used different words, but mathematically, are these essentially the same or are they different? What do you think? Somebody take a guess at it. Emma.
I think they're different because A is talking about out of 20 members, how can you get the top 2 people, like with awards, same principle.
Okay, so I'm going to stop right there because Emma's exactly right. In question A, we're definitely picking someone as president and someone as vice president. So if we were going to draw blanks, that would be 20 times 19, wouldn't it? Okay, so Emma, continue. Thank you.
And then with B, it says in how many ways can they choose a 2-person governing council? That means that they have to like narrow it down to only 2 people, and the rest are like gone pretty much.
18.
But we don't have.
No,
we
same
don't have,
thing. You don't have an
we
exact
don't have an
number.
initial number.
Yeah, no, it's this in how
It's the same
it's the
number.
same. It's the same 20-member class.
So it starts at 20 and then goes
So
to
same
18.
thing.
No, it's not the same thing. And here, I need to help you understand why. This is the hardest part of this whole unit, actually. But think about this for a minute. There's 20 of you. Let's say there's 20 of you in the room. And I am going to pick a president and a vice president. The order that I choose you matters. Would you agree with that? If I'm picking Francie as president and Jalen as vice president, that's different than if I pick Jalen first and Francie second. Order matters. So in this first question, order matters. Now, in question B, I'm picking a 2-person governing
Or it
council.
doesn't matter.
18.
I'm still picking 2 people out of the 20, but the order I pick you doesn't matter. When this is a huge distinction. When order matters, we use what is called permutations. And when you are doing permutations, when order matters, you are welcome to use the blanks like Emma did. She was exactly right. You're welcome to do that. Mathematically, it's written like, oh, not 8. Mathematically, it's written like this, 20p2. The P stands for permutations. And the word permutations means order matters. So Emma did the problem and got, what is that, 380? All right, and we're going to type this in on our calculator. So type the number 20, and then go to where your factorial is. So do math, across the prob, and then look right there in the options. Do you see it? You see the NPR? Press that button, and then press 2, and you should have gotten 380, the same 380. This is the number of total people, and this is the number that you are picking. And this is the strategy you use when order matters. So president, vice president, order matters. When you're just reaching into the pile and grabbing 2, that is called a combination. And that would be written like this. You can't blank this one. You can't do it this way. Because as soon as you put blanks down, you're putting order into the problem. You're saying first, second. Can't do that. So you must type this in on your calculator. You're going to type 20, go to your probability menu, where the factorial is, choose the NCR option, and what's that one?
190.
190.
It's like what? So what?
Yeah, what are the numbers that you want? Is it
What are they combination?
So they're half.
You can't blank it. You can't do that. So it's the formula for it is 20 factorial over 15 factorial 2 factorial. But I'm having you use your calculator.
So 18. So 20 being how many kids we have? 18 for how many we have left, and then 2 for how many we're choosing.
Yes. Now let's look at 27. I don't want you. You don't need to worry about that. Look at number 27.
Is it n minus r?
How many ways can a club with 13 members choose a 4-person leadership team? How many ways can the same club choose a president, vice president, secretary, and treasurer? So for problem 27, tell me the setups. They are different problems.
13, 12.
A will be what?
13 NCR.
No, A will be 13C4. Why is it 13C4? It's a combination problem. Kids, if I say I need a group of 4, I'm going to pick 4 of you. Does it matter who gets picked first? No, you just want to get 4 people. That's combinations. I need a combination of 4 people. I don't care what order I picked you in. This one is 13P4. Because here I am choosing you for specific tasks. So order matters. If you want to be president, you want to be picked first. Here, you just want to be on the team. Here, you care about whether you're picked first, second, or third. And these are different numbers. Anybody got them? What's 13C4? 715. What's 13P4?
17, 160.
17, 160. Okay, so let me repeat real quick before we go to the third new thing we're learning today. The first new thing we learned is if we have repeated items that we're arranging, like letters, then we take whatever the total is, 11 factorial, and then we divide it by the number of each repeating element factorial. Okay? Got it? The second new thing we learned is when we have a group of people or objects or something, and we have a group that we are picking from, there are 2 ways we can do that. We can pick with order, or we can pick with no order. If order matters and you're picking, if you are picking with order, you're going to set it up as a P problem, a permutation problem. If you are picking and order doesn't matter, then you are doing a C problem. And We're just going to read each problem carefully and try to reason that out. It does require some thought, but I have confidence in you. The last new thing we're learning, and we're only going to get through one of these problems today. The last new thing we're learning has to do with expanding binomials. Okay? So, I didn't leave you very much room, but somewhere over to the side, I need you to squeeze something in for me. I need you to squeeze in this set of numbers. And I would like you to write them down as neatly as possible, arranged the way that I've arranged them. It looks like a Christmas tree. It's a triangle of numbers. It's actually called Pascal's triangle. And Corey asked a minute ago, are we going to be talking about probability? Pascal's triangle obviously was developed by Blaise Pascal, and he was a great mathematician. We have a computer language called Pascal, named for him, but he was odd. Most of the really great mathematicians were odd. Pascal was odd. He ran with kind of a not so reputable group of people. They were called gamers. They gambled. They were gamers. And they knew Pascal was brilliant, so they went to him and said, hey, help us win. You understand, you're smart, you get it. Help us win these games that we're playing. So that was kind of the beginning of game theory. And Pascal started with some of the easiest games of chance, like flipping a coin or rolling a die. So believe it or not, this set of numbers came from the study of coin tossing, die rolling, that kind of thing. We're not using it for that right at this moment, but we will. Here is what we're using it for. When we're expanding to the fourth power, so this guy right here is important. Whatever power that is the row of numbers that I want you to write down. So here's row 1, 2, 3, 4. And you can kind of tell that from the second number in the row. Now, this is called expansion for a reason. So I want you to spread them out. But there is the fourth row of numbers. Now, tomorrow, if we have time, or whenever I see you again, I'm going to talk to you about where these numbers came from, or how you can build these numbers.
It's Wednesday. Oh, I thought that was Friday.
No, these are the numbers that we're using. Okay? You don't need to memorize them. I'm going to show you how to build it. But, you can memorize it if you want. Next to each of these numbers, I want you to put an X and a Y. So I want you to put an X and a Y. And let's get used to putting them in parentheses. So X and Y next to each of these numbers. So I've taken the fourth row of Pascal's triangle, spread those numbers out, and next to each one of those, I have written an X and a Y because those are the two parts of my problem. This is a binomial, two parts. Now, yours might be a little more crowded because you're operating on the confines of the paper. Let's put nice big plus signs between each grouping because I want to make sure the groups don't run together. Mrs. Ford, will we always put plus signs? Yes, we will. Yes, we will. There might be negatives involved other places, but we're always going to put plus signs to separate our groupings. Okay? Now, we are multiplying to the fourth power. So right here on this X, look where I'm pointing, I want you to put a 4 on the X. Now, I'm not randomly putting a 4 there. I'm putting a 4 there because it's to the fourth power. And then this one's gonna get a 3, and a 2, and a 1, and a 0. So I put my powers on the X's, starting at the beginning with 4, and counting down. Okay? Now I'm down here. So I'm gonna do the same thing with the Y's, but backwards. So 4, 3, 2, 1, 0. Notice that each grouping has a degree of 4. In other words, if I add up the exponents of each group, I get a 4. I'll get that number if you do it right.
They made this up.
So I started with X's, the first number, and went 4, 3, 2, 1, 0. And then the second number, I did the same thing from the other end. Now I'm going to simplify. What is anything to the 0 power?
1.
So this first term is just x to the 4th. Would you agree? That one is just going to be 4x cubed y. Nothing simplifies there. Or here. Or there. What about that last term though? I think we can simplify a little bit down there. What's that last one going to be?
Y to the 4th.
Y to the 4th. And this is the expansion. Now, that's your answer.
You used to do that for every problem.
Well, yes, but Jack, your alternative is FOILing that out 4 times, or if it's a 6, FOILing it out 6 times, or if it's a 12, FOILing it out 12 times. Okay, I'm going to show you how to build it. You need to be able to use Pascal's triangle, but it's really easy to build. Everybody pay attention. Last thing, I'm going to show you how to build this triangle of numbers. It's not magic. You got to remember we start with a 1 and a 1. Then remember that every row is going to start and end with a 1. Okay? So I'm going to erase all this middle part because this is the part we have to memorize. 1, 1, 1's on the end. Add these 2 together and put the number here. Add these 2 together, these 2 together.
Oh, that's interesting.
Pray.
Holy Mary, Mother of God, pray for us sinners now. Holy Spirit,
Yes, I need my calculators back.
we can't thank you.
Nobody goes till I get all my calculators back. I gotta bring them out here.
Until I get a hug.
Yeah, fuck that.
This is the day the Lord has made.
Whoa, who else has my calculators?
I do, but I left my freaking jacket.
I got one more out there. Wait.
Almost Johnson has. Almost Johnson has. Hey, best of luck, Maddie. Best of luck. I'll send a prayer. I'll send a prayer. You gotta cross from the guy. Gotta kiss before you take the test.
Because you're gonna tickle me and I'm not down for it. Yours is on the You go.
No, she's staying.
Oh, okay. I just working for you. I'm like,
No.
And I just talked to the mayor. She said he is. I need to get his campsite.
she wouldn't be on the list.
She
because
would be.
might
Yeah, I just wrote them both down because I wanted to make sure that they truly got moved over. I hope all that makes sense. And this is just the same thing as what I put on the paper.
God bless you, Mara. I'm sorry I chased you out of the bathroom.
No, that's okay. Thank you.
Okay, what do you want? Yeah, God bless you. Okay, what did you have in mind?
I just get into my dress and take pictures now. I was
Go ahead
sick.
and do that, yeah. Go ahead.
Please, I need a weekend off.
What are you gonna do something?
Yeah,
6-1 to 6-3. You have yesterday's test. What are you here for?
Yesterday's test.
Why, Emma? You too, sweetheart. Let's use the study and. All right, so 6-1 to 6-3. Bye, you're not here to do something?
No.
Bye, Chandra.
Wish me luck, we have tractor today.
Okay, go
See you,
team.
guys.
At least it's not raining.
Yeah.
Oh, Maddie, can you turn off the video?
Yeah.
I think it's still running. Okay. So here.